welcome to RF transceiver design course. We are discussing the transceiver architectures. In last class we have discussed the Hilbert transform and Hartley architecture and how we can use a Hilbert transform in order to reject the image. So now one of the another class of the image reject receiver is a viewer architecture. So we will see the viewer architecture in detail. So the difference between viewer architecture and Hartley architecture is, in Hartley we are adding a 0 or 90-degree phase shift by using any RC/CR filter, and that we can also do at the baseband side. However, in viewer architecture we are doing the down conversion 2 times. So it is a version of super heterodyne version where we are converting the signal 2 times down conversion, and we are adding the 90-degree phase shift by doing the same quadrature down conversion again. So it will add the 90-degree phase shift. So up to this point x, a and b we have already derived how the signal will be down converted. So if we try to see the trigonometrically at C and D how the signal will look like. So again omega LO1 and omega LO2. So here omega 1 is omega LO1 and omega 2 is omega LO2. So and omega C is a input RF frequency. So this is omega C minus omega 1 minus omega 2. Now because we are doing the multiplication 2 times cos omega L1 and cos omega L2, it is a signal divided by 4 and there is some phase of the signal. Similarly, there is another component which is the image minus omega 1 minus omega 2. Now when we multiply omega with omega LO2, what is happening that its positive term is also coming and negative term is also coming. So this is a omega 1 minus omega 2, that is a negative term, and this is a positive term, that is omega C minus omega 1 plus omega 2, omega m minus omega 1 plus omega 2. So same thing at x dt, we are multiplying with sin omega LOT. So the sign will change as explained in the Hilbert transform, that minus a signal by 4 cos omega C minus omega 1 minus omega 2 plus phi signal minus a im by 4 cos omega m minus omega 1 minus omega 2. So and this is a positive term. Now if we take one example, we will understand that how this positive term can be filtered out. So if your omega carrier frequency, let us say it is a 1000 megahertz and your omega 1, let us say that is 600 megahertz and omega 2 is 300 megahertz. So what will happen, that the what is the omega IF? Omega IF is equal to omega C minus omega 1 minus omega 2, that is a 100 megahertz. Now if we consider omega C minus omega 1 plus omega 2, so that is 400 plus 300, so that will come this term will come around 700 megahertz, and same thing this will be minus, so that is a part of image. So this will be too far from 100 megahertz, so that we can easily filter out. So we can neglect these two term from here and from here. So now only the term 4 terms are remain, that is a 2 term at xc, that is omega c minus omega 1 minus omega 2 t plus pi signal, and this is the image. Now because of the quadrature multiplication there is a minus sign here, that is a minus A signal 4 cos omega c minus omega 2. So, if we just considered this one of the frequency, uh, here what we are trying to do, when we do the subtraction of this, one of the term will be cancelled out, that is the image, this image will be cancelled out, and that this signal will remain here. So, this is how the Weaver architecture will work. So, the difference only is here we are doing a 2 times down conversion, that it is cos omega LO 1t and cos omega LO 2t, again quadrature sin omega LO 1t and sin omega LO 2t. So, the difference is the by using a 2 times multiplication we are rejecting the image. Now, another important class of receiver architecture is a low IF receiver. So, what exactly low IF receiver is? The IF frequency is around the frequency of the bandwidth, it is bandwidth of your signal. So, what will happen, the direct conversion of 200 kilohertz desired channel to 0 IF may significantly corrupt the signal by 1 by f noise. So, in direct conversion what is the issue, that we have a problem of the DC offset, we have a problem of leakage, we have a problem of 1 by f noise. Now, all these problem can be solved if we have a sufficient, means not too much IF, but sufficient IF, so that it will down convert the signal, and again we can use the on chip filtering, so that the signal can be easily filtered out and we can also reject the image. So, how exactly the low IF receiver will work? So, here this is the carrier frequency, and at half of the LO, means half of the bandwidth. So, this is a half of the bandwidth, there is a LO signal will be applied, and when this signal is down converted, there is a signal will be here and this is the image. So, this will be the image, and on one side there is a signal. So, you can easily filter out your signal on chip. So, if you consider the GSM standard requires that a receiver tolerate an adjacent channel only 9 dB above the desired channel. So, if there is a adjacent channel just after this is the adjacent channel, then this image will, this is the image, means on other side there is a image and that image will come here. So, what we are interested to remove this image, and how what is the advantage of this, that only 9 dB you need to reject, and you can use a simple image reject receiver which can provide a 30 dB. Let us say if image rejection ratio is a 30 dB, the image remains 20 dB below the signal. So, you can easily reject the image by here it is 9 dB adjacent channel, only 9 dB above the, so that you can easily reject by using the any image reject filter. So, this low IF architecture, it has a combination of heterodyne and homodyne. So, what are the advantage of heterodyne? That it is more accurate, and then homodyne, what is the advantage? It is easily on chip you can make. Now, this architecture, low IF architecture, you can easily make on chip and you can filter out your signal on chip. And the problem of image, there is a, because it is a heterodyne structure, the problem of image can easily be solved if you have a sufficient image rejection ratio by using the image reject filters. So, advantage of homodyne and heterodyne both you can combine in low IF, and this is a very popular architecture in many receivers that are employed. So, and it's provide a very good receptivity, and even you can do the modulation down conversion and the baseband you convert to the digital and you can reject the image. Now, for rejection of image, one of the widely used structure, that is a polyphase filter. So, we will see the how the polyphase filter works. So, in order to understand the polyphase filter, it is better we first understand how the RC will behave if you give the different signal. So, if there is a V1 signal you are applying at the, this is a RC filter. Now, if you are applying a V1 signal at this node and V1 V2 signal at this node, the V out at this node by using KCL you can easily get this equation. What is the V out? V out is equal to V1 plus R1 C1 as V2 divided by R1 C1 as plus V1, that you can easily get if you consider this node as a V out, you can write V out minus V1 by R1 plus V out minus V2 by 1 by SC is equal to 0. Then if you take this on this side, V out minus V1 by R1 equal to V2 minus V out by 1 by S. So, if we take R1 on this side, what we will get? V out minus V1 into R1 C1 into S V2 minus V out. If I will take V out on this side, that is V out 1 plus R1 C1 S, and then what you will get? V1 plus V2 R1 C1 S. So, same thing, this is the same equation which is written here. So, now we will take a two case, that what kind of voltage we apply, means because when we are using a image, we have already seen there is a R plus means I plus JQ. So, there is a imaginary part is going to come there in the image, and how we can use that to reject, how you can use R1 C1 filter, RC filter to reject the image. So, the case 1, what case 1 says, that if I have a V2 at this point, this V2, if we will use a V2 which is equal to minus J V1, and if V1 is a same as a V1. So, in this equation what we will do is write V2 here, V2 is equal to minus J V1, already S j omega is already there. So, what you will get? V1 into R1 C1 omega plus 1 divided by J R1 C1 omega, because S is replaced with a J omega here. And if we consider the omega frequency which is RC inverse, that is R1 C1 inverse, then we will get 2V1 by, because this will be the 1, this will also 1, then 2V1 by 1 plus J, it is nothing but a V1 into 1 minus J. If we write it down, the amplitude of this, it is root 2 V1 and the phase is minus 45 degree. So, what it says, that if you have a, on one side there is a V1 voltage and the another side of the filter there is a J minus JV1, that is then you will get the, so this is a minus V2 which is a minus JV1 and this is a V1, the resultant voltage is V out. So, here you what is happening, that we are getting a V out which is a combination of V 1 and minus j V 1. Now, we will do the another case if it is a positive. So, I will try to erase. So, here in the second case, instead of minus j V 1 we are giving plus j V 1, and then we if V 2 is a plus j V 1, that is a negative Hilbert. So, and then in this negative Hilbert, when we applied, if your omega is equal to R 1 C 1 inverse, your V out in this case, because this is a 1 minus 1 plus 1, this will be cancel out, your V out is just a 0. So, what is the conclusion, that if your V 1 and minus j V 1, if you applied the voltage V 1 and minus j V 1 on other side, your resultant is a V out. However, if you have a negative Hilbert, that is a plus j V 1, then you will have the 0 output. Now, we will try to apply this analogy or this understanding to the actual receiver architecture and how we can reject the image. So, if we extend the topology of previous figure, V 1 and minus C V 1 are available in differential form, and we can construct a image reject receiver. So, in this example, what if you have a plus V 1 and V 2 which is minus j V 1. So, this is a plus V 1 and minus j V 1, you have a resultant output is like this. And if you have a opposite, if this is a minus V 1 and plus j V 1, then only you are changing the polarity of V 1 to minus V 1, and this polarity of minus j V 1 is a plus j V 1, then you will have a V out 2. So, if we try to apply this to the image, so this is a quadrature down converter. We all know that if you multiply with cos omega LO, what you will get, V signal plus V IM. There is no any phase change will happen, minus V signal minus V IM. This what we will get when we multiply with cos omega LO. So, here only amplitude is considered. So, plus V signal and plus V IM, because we have done analysis of amplitude in the last slide. Now, if when you apply with the sin omega LO, there is a plus j V signal minus j V IM. So, the polarity of image will change, and here, so this polarity of image we have also seen graphically in the while discussing the Hilbert transform, and here polarity of this is change, that is minus j V signal plus j V IM. So, here it is a positive and negative, and then there is a plus j V IM. Now, we will try that how it will be cancelling out the image and we are getting the signal. So, if you take a first case, this is the first case, that your signal is at one side of R 1 is a V signal. So, this is a V signal R 1, then there is a capacitor C 1, and on other side what you have, right now we are considering on the signal, only signal, and on other side you have a plus j V signal. So, if you have a V signal and plus j V signal, so what we have done, V 1 and plus j V signal, here when you apply V signal and plus j V signal, what will happen, you will have a here there is a minus j. So, there is a plus V signal, and here because this is coming from this side, it is minus j V signal. So, Always remember that this is a 0 degree phase shift, this is a 180 degree phase shift, this is one is a 90. So, one is this is a 90 and this is a 270. So, here this is connected to minus j V signal. So, I will rewrite it is minus j V signal. So, what will be the V out? This is a plus V1 minus j V1. So, you will get here the V out which is a portion of the V signal which is a 45 degree phase shifter. Now, we take another case, you have a image VIM. So, now we have a image, if we will consider other color, that is a VIM and that is a plus JVIM. So, we already have seen that if VIM is there and plus J means the voltage is a negative Hilbert transform, then your output is 0. So, here your output is coming to be 0 because and your image is a cancel out. Similarly, when you do the same thing here, only the sign will change. So, this is a minus V signal and this is a minus V signal and plus JV signal. If you do the same thing in this equation, if you use the same thing with this equation, only the difference is this V out will be on other side, but it is going to give you the V out 2 like this. So, you will get the V out 2 which is a signal, which is a part of the signal. Now, what will happen with the image? For image you will get a minus what is a minus VIM and then the polarity is both same minus G VIM. So, if the polarity both are same, here also positive positive, here negative negative, that means it will be 0 and that we can easily get from this equation. And R1 your R1 C1 is equal to the your frequency 1 by omega. So, I hope it is clear to all of you that how we can able to reject the image and construct. So, it is a positive construction for the signal and then there is a image that we are removing by using this architecture and this is called the image reject receiver by using a polyphase filter. So, this is nothing but a polyphase filter which are adding the various phases. We can also extend this to the 4 phases. So, instead of a 2 stage only, we can also make a sequence asymmetric polyphase filter and in that what we need to give. So, on one side there is a voltage V1, on another side there is a voltage that is minus JV1. So, this is a V1, then this is a minus JV1, again there is a plus JV1. So, V1 and plus JV1 and then plus JV1 and minus V1. So, if you consider this is a 0 degree, this is a 90 degree, this is a 180 degree and this is a 270 degree, that are the phase shift. So, this is a 0, 90. So, we can also write in terms of the phasor diagram 180 and 270. So, if you and this is also called sequence asymmetric polyphase filter and since the signal and the image arrive at the input with the different sequences, one is passed to the output and other will be suppressed. So, same thing will be applied at V out 2, one will be means your signal will be coming as a V out 1, V out 2, V out 3. So, this is a V out 1, V out 2, V out 3 and V out 4. That are the 4 output that you will get by using this, and we can extend this to the another example where how the image can be cancelled out by RC. So, the only difference is V out 1 and V out 2, you will have output at R1. So, this is at output R1 and here also output at R2, that is V1 and minus V1. So, here you will have a, this is a positive signal and then this is a negative signal. So, this will be considered, this is 0 and 180 and then this is a 90 and 270. So, in order to generate the 4 phases you need a quadrature mixer. So, this mixer will have a 0, 180 and 90, 270 when you apply the sin omega LO t. So, same thing we can also analyze with this here when you get the when you have the signal which is 1, 2, 3, 4, that is a V signal, and only what this is doing that here when you are using a polyphase filter, at that time this signal is rotated 145 degree clockwise. So, this is a clockwise rotation 45 degree and here it is rotated anti-clockwise and it is rejected. So, here there is a clockwise at the output, there is a clockwise it is transferring from here to here and then there is a anti for the image it is a anti-clockwise. So, this is a output which is transferred from here to here, that is a clockwise, however, in image it is a anti-clockwise and this is the way the image will be rejected. And also make sure that here there is a the at this V out 3 and V out 4 there is a change in the C3 R3 how we have connected. So, do not confuse while connecting, you should not connect R1, R2, R3, R4, C1, C2, C3, C4, then you cannot cancel. At V out 3 and V out 4 you need to interchange because your phase are changing. So, this is easily be constructed, R1 is connected to C1, again R is connected to C and we are going to give the input at one side and output we are going to get on the other side. So, this is how this polyphase filter works. Yeah. So, let us say in the previous example both the case what we have considered is omega which is not equal to RC inverse, which is equal to RC inverse, but let us say if your omega is not equal to RC inverse then what will happen. So, in that case if we try to add the omega R1 C1 inverse plus delta omega. So, if there is some change in the frequency, that is a delta change, then what will happen that we have a V out magnitude means is given by this root 2 V signal and this there is a minus tan inverse 1 plus RC delta omega, this is a V out and then there is a change in the angle. Now, this RC delta omega by 2 and RC delta omega which will tell us that how much. So, this is a actual when we have considered the ideal RC, but due to the change. So, there is a phase shift which will happen from that is RC delta omega by 2. So, in 5 by 4 plus RC delta omega by 2 and there is a change in the phase as well, change in the amplitude as well. So, there is a This what will happen that when you consider the image, a small portion, because of this mismatch, because of this change in the phase, and this some of the portion, small portion of image will also appear in the output, and that is why you do not have the uh, full rejection of the image, and you need to consider the image reject ratio. So, how much image that we are rejecting by using this polyphase filter, that is a we can quantify, and we have already seen in the Hartley architecture, that is a image reject ratio, that is input signal to image by output signal to image ratio. So, that will be increase if we do not have that much variation in RC, but in reality we can never achieve the complete rejection, but 20, 30 or 35 dB we can get by using a RC polyphase filter. RC polyphase filter has a many application. It is also used in quadrature generation and various application, and it can also be used as a image reject receiver in the image reject receiver architecture. Thank you. We will continue about the receiver architecture, and also we will discuss about the transmitter architecture in the next class.